I'm glad to introduce my partner, Professor Dr. Dan M. Ionel, which will going to join me today in presenting an introductory of high efficiency motor design. Dr. Ionel is currently the Chief Engineer with Regal Beloit Corporation and Research Professor at UWM, Milwaukee. He has more than 25 years of engineering experience. After completing postdoctoral work in Speed Lab at the University of Glasgow, his industrial R&D projects with Fortune 1000 and FCCE funded companies in the United States and United Kingdom, including electrical machines and drives with power ratings between 0.02 horsepower and 10,000 horsepower. Dr. Ionel holds more than 30 patents and has published more than 100 papers, including 2 winners of IEEE Best Paper Award. An IEEE Fellow, he is Technical Program Chair for the IEEE ECTE 2015 Conference and the General Chair of the IEEE Conference on Electrical Machines and Drives, IMDC 2017. With that being said, I pass the stage to Professor Ionel. Dan, please.
Thank you very much for the introduction, Marius. Good afternoon, everyone, and thank you for attending our webinar presentation. Today we will be sharing from our recent experience in designing high-efficiency electric machines. I will first introduce the subject matter and place emphasis on the need for designs that are that need to be both performance in terms of high efficiency as well as cost competitive. The word "and" is very important in this context. The example presented will be permanent magnet, synchronous reluctance, and permanent magnet assisted synchronous reluctance machines. The next 2 sections of the presentation will cover aspects of formal design optimization and multi-physics analysis. And then I'll hand over the presentation to Dr. Roșu, who will be talking about the ANSYS solution. The material presented today is documented in papers that we have published over the last year or so, and I would like to take this opportunity to acknowledge the contributions and at the same time to convey my special thanks to the many collaborators at the Regal Beloit Corporation, ANSYS Multi-Design Limited, University of Wisconsin-Milwaukee, and Marquette University. In recent years, substantial improvements have been achieved in terms of energy savings and energy efficiency. Considering that 60% of the electricity is consumed by electric motors, and the fact that by far the largest proportion of the cost of ownership of an electric machine is represented by the cost of energy, this provides justification for the recent technological developments. Such developments include variable speed power electronic drives, employing high efficiency synchronous machines, and we have exemplified here in the figure, starting from the top and going in clockwise direction, interior permanent magnet, the so-called IPM, synchronous reluctance, and permanent magnet assisted synchronous reluctance nudges. The examples through the remainder of my presentations will be of these types. In terms of computational effort, we have to keep in mind that variable speed machine drives operate over a range of speed and torque. And as such, performance needs to be estimated in many operating conditions. Shown here on the left, we have efficiency maps for a fan or pump application. And then on the right side, we have the many characteristic points for a typical urban driving cycle. As to to this the fact that performance estimation has to be completed for many candidate designs, and then get a better understanding of the extensive effort involved in the process. In terms of let's talk now a little bit about the performance versus cost curves. From the technical and business point of view, it is essential to establish the nonlinear relationship between cost and performance, so that we enable the strategy and the decision process. When both cost and performance, again the word "and" becomes very important, both cost and the performance, as in losses, have to be minimized at the same time. We can no longer talk about one unique best design, but about a collection of designs which lay on what is called a Pareto front. And here we have an exemplification, 3 of those designs denoted by M1, M2, and M3, all of them belonging to the Pareto front. And the characteristic of the Pareto front is that designs placed here, for designs being part of the Pareto front, improvement in one objective is possible only by allowing a deterioration of the other objective or objectives. We have multiple. This quantifies the typical trade-off in which performance can be improved at a higher cost. And it's of course very important design data. Also shown on this slide, we have figures with some of the latest IPM merged products developed and now available from Regal Deloitte Corporation. An important takeaway is that in a study of this nature and complexity, thousands of candidate designs will have to be considered, and they have to be accurately calculated, and such a process will involve, for example, electromagnetic SEA as well as multi-physics, including the thermal and the mechanical aspects. Now, let's understand what are the risks if we do not do such a study. And we will use the figure shown on the left to better understand the problem. We included in the figure about 15,000 candidate designs that come from the study, a study that involved 3 different topologies. And if one would have done only one design, let's say of the topology B and topology C, and would have been unfortunate that those designs fell within the overlapping region that we see in between the red and the blue cloud, one would have drawn the incorrect conclusion that the 2 topologies are comparable. But in fact, if we look, topology B has an advantage in terms of lower cost, while topology C may have an advantage in terms of lower losses. And this is only if we have 2 objectives, those being cost and losses. But if we add to the problem other objectives such as say torque ripple, then we will see even more differentiation possible in between the topology, and the problem can complicate further if we would be to consider other aspects such as sensitivity to manufacturing, what would happen if we have eccentricities in the rotor in terms of increased radial forces, and how will those affect performance. Now, because so many solutions are involved in the process, into the thousands, and each of them will require multiple calculation, the utilization of parallel computation, distributive solving, or HPC solution is highly recommended. At the highest generic level, a procedure for systematic design may look something like shown here. So we establish the specification, we select one topology, and we'll have to conduct all the analysis for all topologies. Then we do an initial sizing, or so-called back-of-the-envelope calculation, and then we move with the design, preferably with an optimal design procedure that would involve electromagnetic, thermal, and mechanical calculation, as well as highly recommended to study the sensitivity to manufacturing, such as what vibration. And we complete this procedure for one topology, and then we have to go back and do it again for another candidate topology, because in principle, the solution is not known in advance. So again, before we reach a decision, a large number of candidate designs will have to be studied. Moving to the next section of the optimization, here we see the principal elements involved. So in terms of formulating the problem, we have to establish what are the independent variables. And those are, for instance, for example, the dimensions of the lamination. And we also establish what are the concurrent objectives and one or several of a list of many possible performance indices, such as material cost or weight or losses, torque, ripple, specific torque, specific losses, and so on can be combined. And I will have some examples following up, which I think will provide further insight and clarification of the problem. Now, in terms of the optimization method itself, big emphasis has been placed in recent years on evolutionary optimization algorithms because of their superiority in handling large problems involving large number of independent variables and therefore large numbers of candidate designs. These procedures that involve algorithms such as genetic algorithm, particle swarm, differential evolution, are inspired from nature. So they involve multiple generations. Each generation will have multiple individuals. The individuals will combine within a generation as well as with the next generation maybe, and through the progress from one generation to another, we will see an improvement in terms of design objectives as well as a grouping towards what would be the preferred value of the independent variables. And the method we have used extensively and on which we have published is based on differential evolution in different various forms. The first case study looks at a comparison between different types of interior permanent magnet machines. So we built up a parametric model which is able to allow the geometry of the virtue to morph all the way from a rather shallow IPM to a V-shaped IPM and all the way to a bespoke type arrangement. And we have studied two topologies, one being of the 12-slot 10-pole design, the other one being of the 12-slot 8-pole. And here we have for reference the main specification of the problem, which goes for a typical 10 horsepower rating. And we have 9 independent variables. We used about 50 generations. Within each generation, we had about 100 candidate designs. And then we run the design optimization with 3 objectives, all concurrent. So the word "and" comes in between all of them. We looked at minimizing the power losses at the rated load. We looked at minimizing the cost of materials and also minimizing the torque ripple. And we did that under the performance constraint specified here. But when we look at the results, what we see is that the Pareto front now, which we previously exemplified in 2D, on the left side will show a 3D variation with all the 3D, concurrent objectives. And then if we go and we plot in a plane cost versus losses, we are able, for instance, to compare two topologies, and we can see that when it comes to ferrite constructions, there may be advantages and disadvantages with each topology. This is nothing to say, for instance, what happens with torque ripple, what will be the measures to mitigate that, and so forth, which will add further complication to the problem. And those who are interested, I highly recommend the papers that I have listed as references at the beginning of the presentation. So we did this study both for neodymium iron boron magnets as well as for ferrites, and then we took all the Pareto fronts and plotted them on the same plane, of course, versus it shows that comparable Paretos can be derived for all topologies. Another problem that I'll briefly describe is a comparison between a synchronous reluctance machine, which involves the use of flux barriers in the rotor and is shown on the top on the left side, as well as of a synchronous reluctance permanent magnet version that will add permanent magnet in the flux barriers. And when we did this comparison, we looked again at three objectives concurrent at the same time: maximum power factor, minimum badness, which we define as the ratio between the square root of watts of losses and the electromagnetic torque. And you kind of imagine that this also links the ability of the machine to get to really transfer the heat produced due to the losses. And and also minimum torque ripple. And then we plotted the two results for the two machines as scatter plots and identified the Paretos. And we have concluded and actually quantified that through the use of permanent magnet-assisted synchronous reluctance technology, significant achievements can be realized both in terms of improving the power factor, as shown by the red cloud, as well as in terms of minimizing badness. And another typical study would involve then, for this particular configuration of synchronous reluctance permanent magnet assisted. So just to give an idea, the careful modification through the automatic design process of the flux barriers in the rotor and the calculation using the Maxwell software will lead to through the design optimization will lead to the improvement. And we can see the improvements here quantified both in terms of higher specific power for a given core length, as well as in higher power factor. And a final example comes from presents insight. Actually, there are two examples. On the left, we see a study that we did to link the material cost with the losses and the power factor, and to examine what happens with the saliency ratio for an IPM. And we're basically able to quantify the outcome. And on the right side of the slide, we see a comparison of material cost versus power losses when different cooling systems are employed. And we did a study for three different arrangements in terms of cooling, and you can kind of see the big differences, right? So naturally cooled will tend to provide for the criteria specified lower power losses at higher material cost, and at the other end we can go for liquid cooled, which will be of course a smaller unit altogether. Material cost will be lower, but power losses may be higher as well. I'll move to the next section, which presents a few interesting items about multi-physics analysis. But there is a strong coupling and link in permanent magnet machines, and in machines in general, in between the electromagnetic field and performance and the thermal. And one way to think of it, we start with the solid model of the electric machine, and then we do a finite element analysis for the electromagnetic field that will provide the losses. The losses, together with the information we have about the airflow that can be estimated using CFD, will combine to calculate the temperature distribution in the electrical machine. And the temperature distribution will come to be different maybe than the one initially estimated. And if that's the case, it means that the material characteristics will be different than the curve initially considered. In which case we have to go back and do the electromagnetic calculation, and then keep on doing this until we reach convergence in the system. Because we studied very large optimization problems, one pragmatic way to deal with this is to use the minimum analysis analysis capability that will still provide satisfactorily accurate results. And we did that by using electromagnetic FCA, in particular Maxwell 2D by ANSYS for the electromagnetic problem. And then for the thermal problem, we used a software named MergerCAD, which is based on equivalent thermal lumped parameter circuit. The circuit itself is three-dimensional, and it has elements, as it's exemplified here by color liking code, elements for various components of the electrical machine. And in this situation, the power losses for an equivalent thermal circuit like this are representing sources within the nodes of the circuit. This is an approach which is familiar to electrical engineers. This is one of the advantages, and the ability to calculate very quickly is another one, especially when large problems are studied. So there are many complicated aspects when it comes to cooling, ventilation, and I'll only use two examples on the next slide. One comes from the leakage of air through the fins of a totally enclosed fan-cooled nut. In this situation, we have a non-uniform distribution of the speed of the air through the fins, both in the radial cross-section, and we also have the axial leakage. And when we combine this with the nonlinear characteristics of the fan, of the system's resistance, and so on, it gives an idea that this is a complicated problem. And one pragmatic approach is, of course, if experimental data is available, is to calibrate models against that data. Another one would be to use more sophisticated tools such as CFD and so forth. And the next two slides show how the transition can be made from MergerCAD software to ANSYS in terms of solid modeling. And it goes all the way to producing a finite element mesh. And the mesh can be used, it includes also the details on the frame and so forth. And the mesh can be used both for further mechanical analysis or thermal analysis. There are other aspects which are complicating the thermal problem, such as manufacturing. For instance, the interference fitting between the core and the frame produces a resistance, and that resistance has a big influence on the temperature rise inside the temperature distribution inside the machine. Maybe not unexpected to those who are familiar with the manufacturing process, the relationship between the interface gap is what you see here exemplified in the table, and the size of the machine and the technology is not necessarily linear. So again, a method that can calculate quickly and satisfactorily accurate is beneficial in this situation. So now we have one example of user implementation, which we have published, the combination of Maxwell and MergerCAD, and we did that through an ActiveX link within MATLAB. So we took the losses as calculated by Maxwell, and then we, using those losses, calculated the temperature distribution, and we kept on doing until we reached convergence. And when you involve a combination like in between an FEA and a equivalent circuit-based model, what happens then, of course, if we would look at the cycle that involves the two stages, the electromagnetic and the thermal, one of the procedures, the thermal in our case, is so much faster than the other. And it is faster because it's based on a different kind of approach, an equivalent circuit approach. So what we did and a further improvement was possible by noting that the core losses are typically have very little, are less influenced by the change in temperature. And if that is the case, then through the scripting, that was one of the motivations to organize it in the software arrangement you have seen before, we were able to introduce one supplementary loop for the thermal analysis only, with a very simple model for the calculation of losses. slides about mechanical aspects, and they relate to the coupling of forces leading to vibration and noise. So if we start from the electromagnetic forces computed with the Maxwell software, those will enable to estimate the mechanical displacement, and based on the mechanical displacement we can evaluate the sound out, and from there we can have the noise estimation. And such studies are performed, for instance, to study the effect of eccentricity, which may be dependent of topology. And shown here are the radial forces, the modulus of the radial forces for three different machine configurations: a 36-slot 6-pole, a 9-slot 6-pole, and a 12-slot 10-pole design. And then, of course, their sensitivity to eccentricity is different. So this brings me to the next section of the presentation, and Dr. Roshu will take over from here to provide you with more details about the ANSYS solution. I'll be available here for questions at the end. Thank you.
Thank you very much, Dan, and thank you once again for your nice presentation. In the next couple of minutes, we're going to focus on ANSYS solution to explore a little bit, what type of methodology ANSYS is proposing, to properly design an electrical machine from a magnetic, solution going into a multi-physics solution, including thermal and structural design. Advancing to the next slide, this is outlining, the presentation, showing, integrated motor design flow based on ANSYS solution, with focus on electromagnetic and thermal coupling simulation, as well electromagnetic and structural dynamic simulation. On the motor design integration, ANSYS provides a complete design flow that progresses from an analytical design sizing option to more rigorous electromagnetic design, to fully couple electromagnetic, thermal, stress, and acoustic physics modeling. Finite element analysis of the electromagnetics is the foundation for creating physics-based models that are used within zero-D systems for electric drive and power electronics analysis. And the ANSYS workbench, which is a more general platform to integrate multi-physics simulation, can be used to manage multi-physics design and perform system-wide optimization. High-performance computing speeds the solution of electrical machines. High-performance computing for low-frequency electromagnetics speeds up, the entire simulation for any particular low-frequency electromagnetic device, as electric transformers as well. Our talk today is going to be focused on electrical machines, and that's the reason I share with everyone an example of permanent magnet machine, where high-performance study has been applied on a large scale of course. You see here, the speed up coefficient based on 3D transient simulation, and pretty well scalability, provided by multi-core type of simulation. In the same time, we are developing a speed up transient AC steady state solution, being able to achieve steady state condition in the shorter period of time, neglecting all the transients due to the electromagnetic time constant and electromechanical time constant as well. As you see in the right hand side, we have a benchmark study on induction machine for a steady state simulation, and using a steady state simulation including the start condition from zero initial conditions, we've been able to speed up the entire steady state transient simulation by 24 times when employing a new developed algorithm in a Maxwell 2D and Maxwell 3D transient solver. As probably everyone knows already, in 2014, ANSYS Incorporated and Motor Design Limited came together and signed a partnership agreement to collaborate and to build an innovative new design flow, leveraging both ANSYS expertise in magnetic sizing of electrical machines and a motor design expertise in thermal sizing of electrical machines. With that being said, we have been able to implement the first pass to enhance the first pass integration with ANSYS software, including the thermal sizing package from Motor Design Limited called MotorCAD. At this level, we have been able to bundle MotorCAD and ARMExpert solution to fully deploy a complete precising solution for both electromagnetic physics-based solver and multi-physics-based solvers within ANSYS portfolio as ANSYS Computation Fluid Dynamic or ANSYS Workbench environment. In the same time, ARMExpert and MotorCAD can generate a reduced order model for ANSYS Implorer to evaluate the nonlinear dynamics of the entire electric drive system. The magnetic and thermal design sizing solution provided by ANSYS in collaboration with Motor Design Limited. As I mentioned earlier, ANSYS is providing with a template-based electrical machine design from a magnetic perspective, and this package is called ANSYS ARMExpert, generating pre-existing topology based on pre-existing topology libraries, various configurations, and analytical solutions. In the same time, MotorCAD generates various configurations on pre-existing template-based motor designs from a thermal perspective, from a thermal simulation point of view, being able to calculate the heat transfer automatically and provide a detailed cooling system and facilitating optimizations. ARMExpert as the magnetic sizing package provides with 16 plus different topologies, 3D configuration, mainly 3D radial field configurations. However, in the last two releases, ARMExpert has been enhanced with axial field concept, providing wound rotor, axial machine design, as well permanent magnet axial machine design. ARMExpert is enhanced with various editors to enable the user to easily generate a configuration and to fast simulate performance of such electrical machine at the speed of an analytical solver. As we can see, we have winding editor to customize an existing winding topology or customize a winding, preferable winding, configuration. ARMExpert comes with slotting editor with a predefined slot configuration and also adjusting, the option to import a specific slot geometry, a customized slot geometry. Also, ARMExpert comes with various permanent magnet rotor topologies for rotor design configuration. As a new capability in ARMExpert relates to housing, and this housing capability in ARMExpert preview the collaboration with MotorCAD, and we're going to see an example coupling ARMExpert and MotorCAD at the level of analytical solution to precise electrical machine at the level of magnetic performance and also at the level of thermal management performance as well. Based on this type of coupling, ARMExpert been able to generate housing, including pins, ducts, front caps, rear caps, hoods and flanges, customizing properly these elements to be able to communicate with the thermal design from MotorCAD. Moving into the MotorCAD family, and MotorCAD is a template-based solution for electrical machines and includes proven models for an extensive range of cooling types as totally enclosed non-ventilated or totally enclosed fan-cooled, cooling, and so on. MotorCAD provides with the thermal analysis and analytical non-circuit analysis, as we can see in this schematic representation, generating a steady-state thermal solution and also providing with a complex transient duty cycle analysis. As an example of case study, we employ a permanent magnet machine design starting from RMExpert, where RMExpert generates a full magnetic design optimization at the level of pre-magnetic sizing, generating the solid power loss into MotorCAD, and based on exactly the same topology and structure, MotorCAD, we're going to use the power loss from RMExpert as an input for the thermal solution, creating a steady state and or a duty cycle thermal transient analysis. Very important to mention here in this case study, the winding topology is also exported from RMExpert to MotorCAD, and here we have an example of such configuration. The difference on RMExpert and MotorCAD approach, in RMExpert, the designer does not need to know the exact location and the exact distribution of each individual turn within the coil and winding configuration from magnetic performance standpoint, whereas in MotorCAD, a thermal designer needs to understand the hotspots and the hotspots due to a physical distribution of individual turns, individual conductors within the coil and within the winding. This is actually what MotorCAD is able to perform at a higher level of accuracy with the solution coming from RMExpert. Here is an example of a steady-state thermal and also repetitive duty cycle analysis. Just let's stop a little bit here, to understand the difference between a steady-state thermal solution and a repetitive duty cycle solution. Despite of a good magnetic design, the quick thermal solution shows an overheating problem when the steady-state simulation is performed, as shown in this slide. For the same design, if a repetitive duty cycle is applied, the simulated thermal profile shows the suitability of employed cooling system. Using further the MotorCAD thermal network, the newly introduced hybrid thermal model highlights the power of coupling MotorCAD with various other packages within ANSYS portfolio. And here I want to preview a little bit the coupling we've been able to address between MotorCAD and the CFD solution within ANSYS. And this is an example which shows distant lead permanent magnet topology. MotorCAD being able to generate a thermal network, the thermal network which can be imported into ANSYS ISAC solution. To build a complex computation fluid dynamic domain around an equivalent thermal flow network. In such conditions, ISAC solver employs both CFD physics-based analysis outside of the equivalent thermal model and network-based analysis inside of an equivalent thermal network. The equivalent thermal network model interacts with CFD domains by a multi-faceted cylinder, as we can see on the right-hand side. The faces of the cylinder will define the appropriate boundary conditions for the CFD domain based on equivalent network solution. The heat flow and the fluid flow are bidirectional, so the hybrid model will provide with insight of an equivalent model temperature flow profile. And also you can see the difference between a full CFD domain and a hybrid CFD domain and the time computation related to these two approaches. This is a hybrid model and shows the CFD simulation results. We can see the flow tracks around the network for a convection cooling system employed for that particular electrical machine, whereas in the right-hand side we see the nodal temperature report based on the CFD bidirectional integration. Nevertheless, more extensive finite element solution or CFD analysis is required for a very specific type of studies. 3D electromagnetic effects are no longer neglectable. The CFD to check and calibrate the flow calculation is also important, as well as AC loss in windings. In this way, we have been able to integrate the MotorCAD outcome to entire ANSYS workbench environment. Already Dr. Ionel mentioned earlier that MotorCAD is able to export the solid modeling through ANSYS in ANSYS workbench through either design modeler and or spacecraft. Once this 3D geometry is part of ANSYS workbench can be shared among different physics-based solvers. We can develop a low-frequency electromagnetic solution which can be further coupled with a CFD or further coupled with structural type of design analysis. And this is an example of that particular model coming from MotorCAD being enhanced in terms of modeler in ANSYS workbench, including the water jackets and the cooling channel for that permanent magnet Nissan Leaf motor model, and get the complete and detailed CFD solution in ANSYS Fluent based on power loss calculation from transient solution in Maxwell. Moving forward on structural and mechanical type of analysis, the diagram is taken from a reference paper we can see on the lower side of this slide and nicely breaks down the different noise components in electrical machines. The main sources of noises and vibrations in electrical machines are magnetic source, a mechanical source, an aerodynamic source, and electronic source as well. Each individual source of noises in electrical machine has a specific, frequency range spectrum. Just for convenience, I want to remind everyone that 20 Hz to 20 kHz range is a human hearing. 60 Hz is electrical transmission frequency in the United States and 50 Hz is electrical transmission frequency in Europe. 260 Hz is the middle C on a piano. 4 kHz is the highest note on the standard piano. 5 kHz is a common PWM switching frequency which can be applied as a citation signal for an electrical machine drive. In this analysis, we're going to go into detailed type of simulation related to magnetic source of vibration based on radial, generation, slowed harmonic, and magnetic antennas. Overall simulation shows the Maxwell 2D and 3D transient coupling with harmonic stress analysis in ANSYS workbench based on fourth generation electromagnetic force calculation from low frequency electromagnetic environment. Use those forces as input for the structural dynamics and use the displacement versus frequency as input for acoustic field solution. That being said, the magic behind the harmonic coupling is to instantiate the two solver-based components, Maxwell 3D solve, 3D transient solver, and harmonic response solver into ANSYS workbench to share the solution from electromagnetics into harmonic design and automatically coupling, creating the coupling between the two physics solutions to transfer the forces from transient into frequency domain by performing an FFT, and then coupling the two different geometries, including symmetries, coupling the two mesh topologies, and automatically applying the amplitudes and phases before getting the harmonic responses. In this analysis, all nodes as well the structure response vary sinusoidally. at the same frequency. A typical harmonic analysis will calculate the response of the structure to cyclic loads over a frequency range, usually sine sweep, and obtain a graph of some response quantities, usually displacements, versus frequency. The peak value responses are then identified from graphs or response versus frequency, and stresses are then reviewed in those peak frequencies. This is an harmonic response contour plot where a deformation plot at certain frequency is displayed on a color shaded plot. This is a case study where we can definitely see an eccentricity model. And I'm glad to say here, that we continuously improve electromagnetic solution to get more accurate and more representative data into mechanical environment to be able to calculate more accurate and to predict more accurate any vibroacoustic simulation. And here we are talking about static eccentricity, and we are looking at the left-hand side and the right-hand side of the tooth, where the diameters and the air gap, the clearance between the rotor and the stator side, is different. At this level, we build two different cases. The first case includes no eccentricity. That means the center of rotor rotation is the same with the center of the motor, no misalignment. And the second case where we provide 50% static eccentricity, where we'll be creating unbalanced electromagnetic forces. Here we can see an interior permanent magnet acoustic design showing the flow in the workbench moving from 2D transient, magnetic transient solution into structural dynamic solution, and moving into acoustic field solution based on deformation versus frequency output. We move from time domain to frequency domain by performing appropriate FFT in terms of amplitude and phases into the harmonic dynamic simulation and properly integrating on the path segment between the stator and the rotor side. These are the few qualitative results obtained on an interior permanent magnetic acoustic simulation. In the left-hand side column, we see the modal analysis representation for three different modes of oscillation, and on the right-hand side, we see the structural harmonic simulation with, a pressure calculation on an acoustic, simulation. What is also important to mention here, this coupling of acoustic simulation relates to the electromagnetic forces generated by a magnetic design, and that is called vibroacoustic simulation. But also, we can employ an aeroacoustic simulation if we're going to be able to import the displacements coming from a fluid flow due to the cooling system design simulation. With that being said, this is a summary of our today's presentation, providing with a comprehensive optimization to ensure robust design, as been mentioned by Dr. Ionel in the first part of this webinar, followed by a comprehensive electromagnetic thermal and electromagnetic structural dynamic coupling design to complete the multi-physics methodology of an electrical machine simulation. This type of methodology is available not only for permanent magnet machines. The permanent magnet machines, they were the case study we presented during this webinar, but we can employ the same strategy for other type of electrical machines as induction machines or squirrel cage induction machine, or wound rotor induction machine as well. Axial field, transverse field type of machine concept. With that being said, I thank you everyone for attending this webinar. We're going to be open for a couple of questions on our Q&A session. Not before mentioning again that this webinar has been sponsored by Coil Winding Expo, which Coil Winding Expo Chicago is the North American leading event for coil winding, electric motors, and transformer manufacturing technologies. With that being said, I thank you again, everyone.
Thank you, Professor Ionel and Marius. At this, we'll address your questions. We have a few minutes to go over a few Q&As, and any questions that we are not able to get to during today's webinar will be answered after the event. So if you have any question about any of the material presented this afternoon, simply submit a question via the Q&A tab. If your presentation is in full screen and you wish to submit questions, you will need to exit the full screen view and return to the WebEx event window before you will see the Q&A tab on the right side of your screen.
We did receive a question here regarding, and it reads, induction method is not included in the talk. Does this mean you view it as a low efficient type? And I would like to provide some clarification. That is definitely not the case. My part of the presentation is based on things that we have recently published. And we just published on permanent magnet, synchronous reluctance, and synchronous reluctance, permanent magnet machine. But the induction machines, of course, can be made highly efficient. They have new regulation in place, asking for even higher efficiency, and continuous development is always the case for induction machines.
There is another question in the audience related to any studies including the impact of R in magnets. I'm not sure I'm very familiar with REE abbreviation, but assuming that relates to magnetization, demagnetization, temperature effects on permanent magnets, and further, structural design on permanent magnets on a given magnetic topology. The answer is yes. We are able, to consider all these studies. We are able, to consider, proper demagnetization of previously magnetized permanent magnets and temperature-dependent demagnetization as well. In other words, permanent magnets as real magnetic materials, they are demagnetizing because of both, magnetic loads, the armature reaction and other magnetic conditions in electron machines, and also because of thermal temperature rise in such magnetic materials.
There is another interesting question. It reads, which configuration is more tolerant to heat rise? And of course, that's a very difficult question to answer comprehensively with all the possible combinations and topologies. But what I would like to suggest is ANSYS has a very nice a few slides that will demonstrate what the effect is in terms of the internal temperature distribution on a permanent magnet machine. Should that machine be cooled by air on the outer surface, or should it be cooled by water cooling, or if it would be just simply made in an open construction and just cooled naturally? That shows a few insights. Then we showed a little bit about our study where we looked at the impact in terms of losses and cost using different cooling arrangements. The outcome is that really one has to run a big comprehensive study to come to a definitive conclusion, because one solution does not necessarily fit all. Yes, it depends on the application, depends on the ranges considered within and of the specification as well.
Thank you, Dan, for this clarification. Another question from audience. Can you please clarify whether ISAC can be used also for motor modeling thermal simulations? The answer is yes. ISAC is also a CFD solution for electron machines for low frequency electromechanical devices like electron machines or electron transformer and so on. I showed that example for a LEAF PM machine where we can use either a complete CFD domain to analyze natural convection and other cooling algorithms in ISAC, but also to embrace a hybrid model, importing a thermal network from MotorCAD and enhancing this equivalent thermal network with a CFD domain outside for cooling design. And for the next release, we're going to be able to have a coupling between RMXPET and ISAC, and also we're going to be able to generate a complete ISAC project from material assignment, boundary excitation conditions, and static or transient thermal simulation.
I did receive another very specific question, and it reads, how to select an optimal solution among hundreds, if not thousands, of Pareto-front solution. And I want to first to clarify the definition of the Pareto. If we would be to turn at one, I have one slide. I don't know if we have the controls to go back. I have one particular slide where we showed the it was the end of my slide of presentation. Okay. So hopefully it will come here on the optimization. Okay, so if we look here, the Pareto front, strictly speaking, is only represented by the boundary identified with black color on the top left graph. That's the only Pareto. So although we calculate thousands of candidate designs that are included in the scatter plot, the Pareto that has the property that improvement in one objective can only be achieved through a deterioration of the other objective has far less designs. So maybe in this particular example, somewhere in the range of 50 designs in the Pareto, any of the 50 designs will be, strictly speaking, will be a best compromise. Or I shouldn't say best, it will be a compromise design. It will have advantages and disadvantages in one or the other of the objectives. The method of selecting them by themselves, what would be the most important, they can be either biased by the business, the marketing, the technical decision, or they can be done mathematically. And in actual fact, we did publish our first research on the topic, I think a year ago at the ECCE conference, where we took the Pareto front only, and then we took a statistical analysis of that Pareto front to identify from it what are the significant variables and what can we learn from the grouping of the results in that Pareto front.
Thank you, Dan. Before concluding, this webinar, I'd like to mention to everyone that the record of this webinar is going to be available. We're going to be available for your convenience, and also we're interested, to obtain a set of, slides from today's presentation. Please send us an email, and we're going to be able, to communicate with you properly. And I'd like, to conclude this webinar, thanking again everyone for attending this webcast, and also thanking very much, Dan, for your availability and your kindness, to come and present your work here. Thank you very much again.
Thank you very much for inviting me, and to everyone for attending. Thank you.
Thank you, Professor Ionel and Marius. Ladies and gentlemen, this concludes today's webinar. On behalf of ANSYS, I would like to thank you for your attendance today.